Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open fifth session of the year 2024, session 84 of this seminar. Today we have two excellent speakers, Abderrahmane Habbal and Susanne Lenhart. Introducing Abderrahmane Habbal, we have to Professor Anna Dubova. Thank you, Anna. You can start.
Okay, thank you, Juan. It's a pleasure for me to start the first session of the year. It's an honor for me to introduce Abderrahmane Habbal from the University of Nice, Côte d'Azur. Abderrahmane Habbal defended his PhD thesis in mathematics at the University of Nice in 1990. He then worked as a researcher engineer for 2 years, during which he developed the shape optimization code for aerodynamic for Renault automobiles. Subsequently, he held a position as an associate professor at the University Côte d'Azur in France up to the present day. With Gian-Anthony Desideri and Jean-Paul Zolesiu, they founded an in real-time project where he currently conducts his research activity. His research focused on the analysis and optimization of systems governed by partial differential equation, particularly from a multi-criteria perspective, and more recently in the central setting, where he explored new formulations through game theory. The application of this method span nonlinear mechanics, mathematical modeling in biology and medicine, and the inverse problem. So his presentation today will be about strategy for boundary data competition coupled to shape and distributed parameter identification problem. Please, that you can start.
Thank you, Anna, and thank you to the organizers for your kind invitation. I am very pleased to give this talk at this occasion because it is the occasion for me to say something about how a new point of view on old or on classical problems can yield interesting added values. So my talk will be organized as follows. So I start with introducing the general context of this talk. I am interested in PDE constrained inverse problems, and in those family of inverse problems which are known to be severely ill-posed and also very challenging from the computational point of view. And these families, two families of inverse problems, are the first one, which is also known as Cauchy data, is the recovery of missing boundary data. I will say a few words on what I mean by recovery of missing boundary data. And the second family of problems, which is more classical in the inverse problem setting, is the identification of distributed parameters or of shape geometrical items from where like the shape of the domain where the PDE is evolving, or like inclusions or obstacles inside this domain. And for these two problems, among the most challenging tasks that are faced by the inverse problems community, of course, apart from the theoretical questions, are how to design efficient algorithms, which will be algorithms that can handle only a few amount of measurements. And with these measurements, recover the missing data or the missing, the unknown distributed parameters. And the second challenge that is faced by inverse problem community, which can lead to very, to quite difficult and deep theoretical insights is how to design robust algorithms, which could be stable with respect to noisy measurements. And in this talk, I will address the coupled problems. That is, I will set up problems where I want to recover missing boundary data and at the same time, simultaneously, to solve for identification of distributed parameters or shapes. So let me first give a very short motivation, practical motivation for why do we need to have a look on the coupled problems. So this motivation is related to cardiac electrophysiology. So you see here a patient which is wearing an electro vest, and this electro vest is made of sensors, and the sensors wrap all the chest of the patient, and these sensors are made of emitters and of receptors. So the electro vest will impose an electric potential on the chest, and at the same time it will measure the induced electric current intensity, but only on this vest. And of course, in cardiac electrophysiology, we are interested in the electrical activity of the heart. And the heart is not accessible unless we do invasive surgery. So here we have led this model study. We use an MRI with a simplified model of the MRI. So you see colors, different colors are for different components of the body. And we have fat, cavity, and lungs, and the heart. And here we consider the heart as we are only interested in the electric activity inside the heart. So it is very rough approximation, but it is for illustrating illustration we want only to illustrate our method. I am not saying that the electrophysiology is really done this simplified way. So with our methods, we are able to recover the electric potential on the boundary of the heart, which we call inaccessible boundary, with the measurement of the potential and of the electric current, and on the outer boundary, which we'll call later the accessible boundary. And at the same time, we are able to recover electric conductivity of organs. In practice, doctors know an approximate value of these electric conductivities, which are very patient variable. So they differ from patient to patient, but they have like nominal average values for it. And indeed, they told us that if they knew only 30% better these values, they could reconstruct with much more accuracy the electric conductivity, the electric potential on the heart. And here we show results where we recover the electric potential on the inaccessible boundary, which is the circadium of the heart. And also we are able to recover electric conductivity of the lungs, which we assumed it was unknown, with some stability with respect to noisy data. If we have noisy electric potential or noisy current, the measured current here, we still are able to have some stability of the results. So the remaining of the talk will be devoted to some mathematical settings of these questions and how we tackled them. So let me start by saying a few words on what is a data completion or what is data recovery, boundary recovery. It is also known as a Cauchy problem, but indeed it is an inverse problem. And it is stated as follows here for Poisson equation. Here I assume that I know the parameter K. So I have a PDE, but it is not a boundary value problem. It is a PDE set in omega, but with over-specified data on only a part, gamma C, which we call the accessible part of the boundary. On this accessible part, I have over-specified Dirichlet data and Neumann data. And this Cauchy problem has a lot of issues of mathematical pathologies known for it, differently from a classical boundary value problem where we would have either Dirichlet or Neumann or mixed boundary conditions, but on all the boundary. And among the pathologies is the ill-posedness, which means that there is no continuity of the solution of this problem with respect to F nor to phi. And there are also some interesting behavior, which is that existence implies uniqueness thanks to a lot of family of unique continuation properties. And also that this existence and so uniqueness happens only for specific pairs of F and phi, which are called compatible data. So just to underline that the definition of compatible data is when there is a solution. So it doesn't help to know that we have compatible data, because it is exactly meaning that we know that we have a solution. And here in what will follow, we would like not only to recover the Dirichlet and Neumann data on gamma I, but we would also like to reconstruct the unknown distributed parameter. Indeed, in my presentations, it will be unknown shape of inclusions. It is the same principles. Okay, so let me just briefly recall what is ill-posed in the Hadamard sense for Cauchy problems. So here you see a nice problem with this Neumann boundary conditions. Of course, if I manage, if I choose AN to be nice enough, I will have AN sine of nx uniformly converging to 0. So the solution for this limit is 0 everywhere, is just u equal to 0 in all R. R2, and indeed the solution shows a blow up when the solution with this term shows a blow up as soon as y is strictly positive, as is shown in this graphic. So we very severely do not converge to 0. Okay, this ill-posedness is known for Cauchy problems, PDE constraint Cauchy problems since Hadamard, and there are a lot of methods that are devised in order to avoid this ill-posedness. And my talk is within this concern. So in the following, we will show how to reframe inverse problems where we have coupled the data recovery with the reconstruction of shapes as Nash games, and then use this Nash game formulation to devise efficient algorithms to solve the games, hoping that solving the games will lead to solve these coupled inverse problems. And to illustrate these two aims, we will focus on Stokes flows. So on Stokes flows where we want to recover missing boundary data, and at the same time, I will focus exclusively on identification of inclusions for linear and nonlinear Stokes flows. Though there are some other results for some other situations, but we focus on the identification of inclusions. Okay, so let me first start with the case of linear Stokes flows. So the problem is the following. We have a domain omega here with gamma c is the accessible boundary and gamma I is the inaccessible boundary. Just you may imagine there are walls here and here, so we are not able to access gamma I, or there is a body or anything that makes the accessibility, physical accessibility to gamma I impossible. And we want to recover the boundary data on gamma I with over-specified boundary data on gamma C. But to make more complex our problem, we also will consider the case where we have inclusions, or could be also obstacles, where we have inclusions which we don't know the number, nor the shape, nor the location. And we want to recover the number of the inclusions, their shape, and their location. So mathematically speaking, the problem can be formulated like as follows. We have here minus divergence of sigma. Sigma is the stress tensor, the fluid stress tensor, classical fluid stress tensor, with incompressibility condition, with the boundary condition on the inclusions, and on the boundary gamma c, where we have access, we can measure the velocity, and we also can measure normal fluid stress or pressure. So we have over-specified Dirichlet and Neumann boundary data on gamma c, and we want to recover U and the normal stress on gamma I, but also the inclusions omega star. Okay, so here let me go further in the formulation of the mathematical game. We first start by asking a very classical question in inverse problem community, is the identifiability. But here we consider the question of identifiability for the Cauchy problem. Identifiability is known and was proved by Alvarez and others in the case of boundary value problem. So we have Dirichlet or Neumann or pieces of them on all the boundary. And here we have only the Cauchy formulation. So for the Cauchy formulation, we followed the proofs by Alvarez and other papers with specifying the proof to the case where we have possibility to apply unique continuity. And it was quite easy to prove that identifiability result holds with the striking remark that it is only sufficient to have one pair, F and phi, to identify the obstacles. I mean, as soon as you have F and phi compatible data, you have only you have uniqueness of the set of inclusions that fulfill this equation, and this will help us in devising algorithms. So now let us go one step further into the Nash game formulation. So we started indeed from classical control formulations. It was known before us that one could take the Cauchy problem here, or maybe the original one. We could take the Cauchy problem here and split it into two boundary value problems, which are here. In one of the boundary value problems, we keep the Dirichlet overspecified data on gamma C, and we give on gamma I, we give the optimal control processor a parameter eta that will control the Neumann condition on gamma I. And we do, in some duality, we do the same for the control of the Dirichlet boundary data on gamma I, while giving the Neumann overspecified measurement on gamma C to the controller. And classical control formulation can be seen as just, I use the pair of control variables eta and tau, and I minimize some functional with respect to eta and to tau, as you will see here, as you will see just after this slide. And what we did was only to say, okay, starting from the control formulation, now I consider that eta and tau are strategies given to players, and each of these players is aimed at minimizing a cost functional that could be completely different from one to the other. So this led us to the following formulation. If I consider here only G1 and G2, if I sum G1 and G2, I get a function that I could control with respect to eta and tau, and which involves the gap with respect to the Neumann boundary condition on gamma C, the gap with respect to the Dirichlet boundary condition, and some regularizing fade-in term. And then the optimal control problem would be to minimize G1 plus G2 with respect to the couple eta and tau. So what we do here is to have a game theoretic point of view. So I consider these two players. One controls eta and the other controls tau. And the first player minimizes G1, which is not the sum of G1 and G2, because the first player considers only the gap with respect to Neumann condition. And the second player has control on tau, which is the Dirichlet boundary condition on gamma I, and wants to fill the gap with respect to the Dirichlet Cauchy data. A very simple remark, let us focus on two. If I do my best to let U2 close to F, then you see U2 has already the Neumann boundary condition of phi. So if I fulfill this condition on gamma C, if I fulfill the condition that U2 will be equal to F on gamma C, and I end up with U2 equal to U because of the uniqueness of U. So the aim in trying to fill in the gap for the first player with phi and for the second player with F is to let U1 and U2 be as close as possible to U. So now I introduce the third cost, the third player. So one of the players, the first player, wants to minimize this Neumann gap. The second player wants to minimize the Dirichlet gap. And the third player, which is aimed at identifying inclusions, indeed he uses a famous cost functional, which is named the Cohn-Vogelius cost functional. It is very popular among all people who do shape identification in this context. And indeed, it worked very well for us. Okay, so I am looking here for a Nash equilibrium. So let me first start by recalling what is a Nash equilibrium. So I formulated it within our context where we have 3 players, we have 3 strategy spaces, and so we have a triplet as Nash equilibrium. And this Nash equilibrium fulfills the following property or condition. So the first eta n stands for Nash. The first strategy, the first equilibrium strategy is the best among all possible strategies of the first player, provided, and everything from Nash equilibrium is in the word provided that the second and third player played their Nash strategy. So you can easily imagine the coupling behind this formulation. Each of the players has incentive to play its best strategy, provided the other has played their best strategy. So this is what is called Nash equilibrium. It can also have an interpretation as a fixed point solution. So I don't go into detail with respect to fixed point of what, but please keep in mind that being a fixed point, it will be difficult to compute. It will carry all what we know for computing fixed points, in particular when we do not deal with contractant mappings and so on. So this is why computing a Nash equilibrium will always be costly. So what do we know really? Very, very few things from the theoretical point of view. So we have proved with the linear elliptic equations, it was Poisson and linear Stokes equations, and only for the completion problem. So regardless of this shape cost, which is awful from the theoretical point of view. So we could prove that there exists a unique Nash equilibrium for the play between G1 and G2, and that this Nash equilibrium, which was always unique, it is always existing and unique, even if the f and phi are not compatible. But when f and phi are compatible, so there is a unique Cauchy solution, then the Nash equilibrium is this Cauchy solution. So the game does the job. The game does always some job, and when there is a solution, it does the job. And we could also prove the convergence of the algorithms, the one that is formulated as proximal alternating minimization, due to Atouche and the co-authors. And we were in the setting where, using these results from Atouche, we could prove the convergence of our algorithms. And from the numerical point of view, they proved to be to yield really very, very strikingly efficient results. So, okay, so that was the simple case of data completion in the linear case. So what happens in the linear case, but with a strongly non-linear cost function? Yeah, because here you can easily see that G1 and G2 are quadratic with respect to eta and 2. Quadratic and convex, and we are in very good settings to have uniqueness, existence and uniqueness of Nash equilibrium. To have existence, and indeed the uniqueness is due to the fact that the game between eta and tau, we didn't look for it at the beginning because we didn't know the word for it, but it has a potential structure, which means that there is a term that is controlled only by first player, and here only by second player, and there is a common term which involves the 2 players, but it is common to the 2 players. And this yields what is called the potential game, and to say it quickly, potential games are not equivalent, but are very close to optimal control problems. So we can have recourse to optimal control theory to have existence and uniqueness. Okay, so let us now go to this three-player problem. So I have no more theoretical results to prove now, but only algorithms. Okay, so this is the algorithm to solve the Cauchy-Stokes problem with identification of inclusions. So we start from initial guessed data on the inaccessible boundary, so Neumann and the Dirichlet data, and we start with an initial guess of distribution of inclusions. Then we pay, this is indeed, this is what I would like to underline here. We pay a lot of energy, a lot of computations to make the completion problem to make it really converge the most we can. So we minimize the Neumann gap cost with respect to eta. We minimize the Dirichlet gap cost with respect to tau. And this algorithm, which is a relaxed algorithm, is able to compute a partial Nash equilibrium, where it is like here in this step one, it is like if we were only performing data completion. Then after having converged the inaccessible boundary data enough, we do a step, we minimize, indeed we formulate the problem as minimizing G3, the shape functional with respect to omega. But indeed we do not really do that for a simple reason, which is that the state equations, which are fulfilled by U1 and U2, depend on omega. And so we have to be very careful in minimizing, like if we do optimal control, if we're doing optimal control with spaces which depend on the control, we have to be careful with that. So we reformulated the problem 3 by getting rid of the direct dependence on omega. And we did this by having recourse to level set formulation. So this is classical method. Let me go quite quickly here. The aim is to start from a formulation of the cost, of the convex cost, where we have explicit dependence on the boundaries, because here Sobolev spaces, involved Sobolev spaces directly, explicitly depend on the boundary of little omega. And we formulate G3 as a function, as functional, which depend on a distributed parameter, which is now the level set, which is describing where omegas could be. As soon as we have a cost that depends on distributed parameters, we can lead the apparatus of all the mechanics of adjoint state and quick computation of the gradient with using adjoint state. And we have the gradient of G3 with respect to phi. With respect to, yes, to phi. And we use, this fictitious time-dependent evolution to lead this gradient to 0. So indeed, what we do in practice is to solve for the data completion problem, then do one step of gradient descent with the level sets. So this is only the adjoint state equations. I will skip it. It is not very interesting. So here you see an example where we have accessible boundary is the left side of this square. Inaccessible one is the right side. And here we have put homogeneous Dirichlet boundary data. And starting from this level set, we are able to capture the inclusion, which is also stable with respect to noisy data. Here, the noisy data are the noisy Dirichlet F, the F data are noisy. And we also are able to recover good results for the velocities here, velocity U1 and U2, first and second components of the velocity, and also fluid stress along gamma I. And we are also able to recover multiple inclusions, and with the same satisfactory stability with respect to noise. Okay. So let us now move to the nonlinear Cauchy stocks, which will be the final part of this presentation. So we started with linear stocks. We observed that our trip was successful in achieving coupled data and shape identifications. And we were, of course, aware that this kind of algorithms, these algorithms are really very costly. So in the linear case, we are happy that they work, but they could be not competitive with other most specifically, efficiently designed algorithms. So we thought to ourselves, why not try to make this algorithm interesting in putting not linear state equations, but non-linear state equations. And we were not expecting to that would be interesting at all, but indeed it happened that it is in the nonlinear case that these approaches can really be efficient. So the nonlinear case we are considering is the quasi-Newtonian Stokes flows. Quasi-Newtonian means that the viscosity is strongly nonlinearly dependent on the velocity. And here we have a formulation of a quasi-Newtonian Stokes flow with, so this is the Cauchy formulation. We have F and phi on gamma C, and we want to recover tau and eta on the unknown gamma I. So these tau star and eta star are unknown, and we would like to recover them. So we started by formulating two state equations, and these two state equations are nonlinear. We have a nonlinear Cauchy Stokes, we have a nonlinear boundary value problem for Stokes here, and here we have also a boundary value problem, but which is also nonlinear. And we use the same controls. We introduce players. First player controls eta, and with the knowledge of F, also of the velocity on the known, on the accessible boundary. And the second player wants to control the Dirichlet condition on the inaccessible part, and has at hand the Neumann, so the fluid stress, the normal fluid stress on gamma C. Okay, so I think I have only 1 minute, maybe, or two to go to. Okay.
You can continue.
Okay.
Some time also. Yeah.
Okay. Thank you.
Okay.
So we also considered the occasion to go back to the control type methods, because we started from the community that were making classical optimal control approaches. And we recasted the optimal control problem into games. So it was for us the occasion to assess the difference between approaches by optimal control and approaches by Nash games. And here you see here the classical formulation, which were present in the literature much before we started application of games to tackle data completion problems. So optimal control means that I minimize one cost functional with respect to eta and tau. So there is a single decision maker and a single cost. And the Nash game is just the contrary. We have two decision makers and they control only partially their strategies. First player controls eta and second player controls tau. And so if we follow the same lines than before, apart from the fact that now we have nonlinear state equations, we have exactly the same algorithm, apart that the solving of the state equation will be much more costly. And so we proposed the following algorithm, which can be seen as linearization or can be interpreted in the game theoretic vocabulary as exchange of information. So here, player one, instead of solving the nonlinear Stokes equation with the nonlinear viscosity term where I have W1, player one is player two shares information on his state or her state with player one, and player one shares information on its state with player two. And by doing this, by sharing information on state, indeed we get linear partial boundary value problems. So with respect to W1, this is a linear Stokes equation. And with respect to W2, this is a linear Stokes equation. And when we put this into iterative algorithms, we will have the previous W2 here and the previous W1 here. And so the problem is then completely a linear problem. And what we were praying for is that while the Nash iterations are converging to a Nash equilibrium, the linearized state equations would converge to a nonlinear state equation, because we are asking W1 and W2 to converge, the difference between W1 and W2 to converge to 0. And so if W1 is equal to W2, we end with a nonlinear quasi-Newtonian Stokes equation. So we did this and it worked. And maybe I can directly go to the most interesting results. So this is control type. This is classical control type result, identification of velocities and of stress. And this is a Nash game approach, but where we solve for the nonlinear two-state equations. And this is the Nash game approach where we solve for linearly, where we have exchanged information on states, which made the problems linear. And I think what can be so here you see that for noise of quite large magnitude, we have comparable performance, comparable accuracy between solving at each iteration the fully nonlinear state equations or solving this linearized state equations. And accuracies are comparable while being always better, much better than the control method. So from the CPU time, we see that the linearization turned out to have some payoff because we spent much less CPU time. This is for a uniform noise, and it is much more striking for a Gaussian noise where we have more than 7 times saved CPU cost. And to conclude, so we said, okay, it works for data completion. Why not trying to solve the two problems, so completion and identification of inclusions in this nonlinear setting? So we reintroduce the conjugalus functional. We do the same linearization procedure where W1 gives information to W2 and W2 gives information on state to W1. And computational results were very satisfactory. Stability with noise, respect to noise, identification, and what about the efficiency with the rest? So here the error on identifying the obstacles, even for large magnitude noise, was quite satisfactory. And we also had the CPU time. So here we have also the same efficiency when we have more than 2 inclusions. And the CPU time, which was comparable between the 2 approaches. And so to conclude, it was very painful in our case to reframe coupled inverse problems within a game theoretic framework. It could yield new original algorithms, which turned out to be strikingly efficient. I mean, the results were very interesting. I think one important point is that using this approach, you can consider nonlinear state equations and do this linearization along while capturing the Nash equilibrium. It is also painful. And the all our algorithms did not show any instability indeed. And what is left is apart from the completion approach, completion problem for linear elliptic equations. What is left is everything from the point of view of theoretical results. Thank you.
Thank you very much for this very nice talk. So let's start with questions. Yes, are there any questions in the audience? You can use chat or activate your microphone.
Yes,
so okay.
Yeah, thank you for your interesting talk. It was very nice. I was wondering if you have tried to do something like a Pareto strategy, or you know, you have different Stackelberg strategies, so you may have different kind of hierarchical attacking the problem, and Nash is not the only one. So have you tried to do that? Have you think about that?
Thank you for this very interesting, very important question, because first it opens the door for what is really behind my approach. We started this approach several years ago, and we kept ourselves within this static complete information Nash games. So in the non-cooperative case, this is only a class of games. And indeed, my aim was to say, okay, we should investigate much more frameworks that exist in game theory. Among these frameworks is the incomplete information case and the dynamic case with first example of dynamics is the leader-follower case, where you have this Stackelberg equilibrium as a possible solution. Of course, if we consider Pareto case would indeed G1 and G2 are really concurrent. I have plotted what happens to G1 and G2 while these players were minimizing one G1 and then G2, and indeed they are really concurrent. So, and they end up in one point, which was the Nash equilibrium point, which also was the Cauchy solution. So there is no Pareto front indeed.
Okay, okay.
But for Stackelberg, the answer is much more complex, sorry, because let me go up to algorithm. Okay, like this one. We could have considered a Stackelberg game where omega is the leader and eta and tau are followers. Or the converse, or consider eta and tau as the leaders and omega the follower. But let us consider omega as the leader. So omega as the leader, if we follow a Stackelberg equilibrium, we should have at hand the map that maps eta and tau, the optimal eta and tau in function of a generic omega. And that is too costly to compute.
Okay. Okay, so maybe theoretically you can do something, but not numerically.
Yes, yes, absolutely, yes, yes.
Thank you very much.
You're welcome.
Okay, are there other questions? One is telling that the audio is open for the question from the audience. Can I ask some question while people is thinking? So I wonder if you can extend these techniques to other problems. For example, from the fluid mechanics, let's think about Navier-Stokes nonlinear system, or probably coupled Boussinesq or some related system. Do you think that this method will work for other kinds of systems?
So Marwa Oni, which was our PhD student, indeed she did the Navier-Stokes case,
Mm-hmm,
the laminar Navier-Stokes, the steady one, and in her thesis she presented some pieces of Navier-Stokes. So at least from the computational algorithm, from the algorithmic point of view, yes. Now, from the theory, from the theoretical point of view, indeed, the problem is the following. Okay. Okay, let me go. I won't say a word about the theoretical aspects when when omegas are involved, because even the direct problem is difficult. There are some conjectures from Setien and others, but okay. Let me go to the data completion problem. The data completion problem in the nonlinear case, even in the steady nonlinear case. So if I take here the cost here. If I want to be as close as possible to the framework of Laplace equation where we proved existence and uniqueness, that would be this case, the linearized case. But so I have linear PDEs. So I am very close to, I have elliptic linear equations. I'm very close to use previous results. Apart that by doing this linearization, I destroy the potential structure of the game, because now I have this cost where you remember a potential structure is when player one has an own private cost plus a shared cost. So we still have this shared cost. So this is W1 minus W2 here, and W1 minus W2. So this is shared. This is dependent only on W2. But here I have destroyed the dependence of this term with respect only to W1. And I have no more at hand this very convenient tool of potential structure. So yeah, the job is still to be done theoretically to prove existence and uniqueness of Nash equilibria for nonlinear state equations.
Okay, thank you very much. Are there other questions? Juan? Just a small one, just probably natural, and a question about evolutional problem, time dependence problem. So
yeah, we didn't indeed to play Nash games where state equations are time dependent is the same as doing optimal control with time dependent problems. You just have to reformulate G1 and G2 in taking into account the time dependence, and so you define running costs instead of static costs, and you integrate over time. This is the simplest way to do Nash games. So this is differential games. We look for Nash equilibria for differential games. Yes, it is possible to do so, of course.
Okay.
Yeah.
Okay, so thank you very much. If there are no questions, so let's thank the speaker, and thank you very much.
Thank you for the invitation.
Okay,
Thank
so
you very much.
we have a problem. Well, Susan had a problem, so we need to reschedule her time.